Hello, my name is Henny VanLanen from Wageningen University, the Netherlands. I appreciate that you have decided to take some time to listen to our talk. I will share with you some thoughts about implications of multi-drought definitions to identify streamflow drought across Europe. Let's take off.
First of all, I would like to acknowledge the major contribution of my co-author Samuel Sutanto, who also is working at Wageningen University. The aim of our talk is actually to provide a comprehensive overview of the differences of drought in rivers, and that includes characteristics like the drought occurrence or the frequency, the timing, so that's the timing of the common onset, the average duration, and the deficit volume. We will use a number of identification approaches which are commonly applied, and we will apply that to the pan-European network. The motivation for this project came from the Anywhere, it's a EU Horizon 2020 project that finally last year finished, and a main task in that project was the development of a pan-European multi-hazard early warning system, and that includes a drought forecasting. When we started actually the project, we were asking the end users in the project, water agencies, national and regional, and also the EU, these authorities, we asked what kind of drought indexes would you like to have forecasted. And at that time they were not clear on that. So then we decided actually to implement a number of different drought identification approaches. As we know already, when we started at the project, we know that if you apply a different drought identification approach, then you get different values for your drought indices. Here a couple of papers on this topic already in 2006. Arnold Fleck worked on this, but they only used the fixed threshold, and they focused more on pooling procedures to avoid minor droughts. 2017, Benedict Hoydorf and Kirsten Stahl worked on it, and they compared the fixed and variable threshold. And then a more recent study from the Greek team, they used one catchment in Cyprus to explore what happens if you apply the fixed and the variable threshold, but also daily and a monthly resolution. What according to us is still missing is actually, and that's the reason we did this research in the Anywhere project, is an application of both threshold and standardized approach. So these two different categories which are frequently used in the drought community. And what is also missing is a kind of a systematic overview at the pan-European scale. So this is our domain. That's Europe, as you can see. You see the network of the major rivers. We use more in the analysis. We'll come back to that later. And what you also see is the major climates of Europe. We try to find out also if there is an impact or an effect of the climate on the difference in drought identification approach. You see also four catchments that we studied in more detail. And for this presentation, I will use some data of the Rhine catchment. Is a river network point just north of Cologne in Germany. This is the procedure we use. Actually, we would have been happy if there were observed river flow data and a dense spatial density, so network and sufficiently long records. But these don't exist in Europe, so we decided to use proxies for observed data, and that's simulated time series, which is commonly used in these kind of approaches. We use the list flood model. It's well known from drought monitoring and drought forecasting, also for flood forecasting in Europe. It's a rainfall runoff model with the typical buckets. It is driven by meteorological observations, the known common ones, and these are graded on a 5 to 5 kilometer grid, so there's a very detailed scale for a continent. So what this list flood model is doing, it provides actually stream flow records on a daily basis. For this study we used the period 1919 2018, so almost 30 years of data. So for every river cell, and we actually are dealing with about 30,000 river cells cells, we get a Streamflow record from 1990 to 2018. So after the first step, we go into the second step, and that's the drought identification. So we use a number of different drought identification procedures. That's the standardized one. For this one, we use the standardized Streamflow index aggregated over 1 month. So we need to estimate the parameters of the probability distribution giving these records. So for each record you will do that, and we also applied the threshold, so you have to find daily and monthly thresholds, fixed and variable. So if you have these, then you confront the time series with these for each cell with these thresholds or the parameters of the probability distribution, and then you get the Streamflow droughts over the period 1990 to 2018. So as I said, we used the Lisford model with credited meteorological observations to obtain the streamflow. And the identification methods we selected are listed below. We used the threshold Q18, means that the flow is exceeded in 80% of the time. So the river is in drought when the flow is below the Q80. What we also do is to avoid minor droughts. We actually applied a moving average, so a 30-day centered moving average to avoid minor droughts. Here we have the different identification approaches. So we use the variable and the fixed, so on a daily and on a monthly resolution. And the fifth one is the standardized Streamflow index aggregated over 1 month. Then there was one challenge to find actually the value of the SSI that is actually more or less similar with the Q80, and according to the literature that's minus 0.84. So it means if the SSI is below minus 0.84, then the river is in drought. So, and then if you have these drought identification, then we actually determine these drought characteristics, the frequency, timing, duration, and the deficit volume. Deficit volume can't be determined for the standardized Streamflow index because it's not in the concept. So here's some first results, as I said, for the river Rhine. What you can see here is on the left, you see the daily outcome for the daily approaches, and here for the monthly approaches, we selected the period early 21st century, and we know there was a major drought in 2003 in many places in Europe. So if we zoom in, then we see here the different droughts, actually, of the results of the different drought identification approaches. Here you see some variable threshold droughts where there is no fixed variable drought, and here we see fixed variable droughts, and there are some less intensive droughts. These are both occur both as the variable and fixed threshold droughts, and here you see a variable threshold drought. This is for the daily data. If you look to the monthly data, then there is the SSS1 is added, and you can see it here. There's also the standardized Streamflow index, also the identified drought. It's only shorter than in the monthly fixed and variable threshold method. So actually we apply this technique for all of these 30,000 river cells, and then you get these kind of results. What you see here, maps of Europe with droughts in the river network. Here is the number of events of this historic period, and we applied a different drought identification approach. Here we have the daily approaches, variable threshold, fixed threshold. Here the monthly approaches, the variable threshold, fixed threshold, and the SSIS 1. And if you look to differences, you can see at the first glance that the daily methods actually generate more drought events, clearly more drought events. And you see the brownies and reddish colors here, there are more than here. So if a closer look, then we see this. Here we have two of these 5 maps. This is the variable threshold, and this is the variable threshold on a daily scale and on a monthly scale. And it's clear if you look to these differences that in the upper one there are more drought events than in the lower one. There are about 50% more droughts than here. And of course you can argue if this is not caused by short-lived droughts, and that of course what we did is a kind of a sensitivity analysis, and if we leave out here the droughts which are shorter than 30 days, then we get a reduction in the number of droughts in the northwest, west and central part of Europe, it's about a reduction of 60% in the number of events, and here it's lower, it's about 30% of the events. So minor droughts is an issue if you compare. If we look to the difference between the fixed and the variable threshold, then you see here differences. This is the variable threshold, and the fixed, it's on a daily basis, and then you clearly see here more drought events than if you use a fixed threshold. Here it's about 20% more droughts than when you use a monthly threshold. So what we did for the occurrence, so for the frequency, we also did for the other characteristics, and that's presented here. That's the average drought duration, the deficit volume. Note again that it's not possible to do that for the standardized approaches, and here we have the timing, so the common months of onset, and what you clearly can see there are differences in the maps. Let's have a look at a summary of these maps. What you see here is the table with results. Here we have the daily approaches in the upper table. In the lower table are the monthly approaches. We have done that for the different major climates in Europe. And here we have the variable threshold and here the fixed, the same here on the monthly resolution, and we have added here the standardized Streamflow index, which is only can be applied on the monthly time scale. Let's have a look at some results. What you can see here, and as already said in the previous slide, we have clearly more drought events on average in Europe if we apply the variable threshold versus the fixed threshold, is about 20% more. If you look to the duration, that's negatively correlated, so that fits well. So then here we have more events, so then you have shorter droughts than you have here. If you look to the deficit volume, the result is a little less clear on the base of Europe. They're almost equal. But if you look to specific climate areas, so here is the continental climate in Europe, then it's clearly different. Here it's higher by the variable threshold than by the fixed threshold. If we move on to the monthly time scale, and if we compare these two, that's already what we did in one of the previous slides, and you see almost twice as much drought here than in the daily scale, in the monthly scale, sorry, and this a little bit less here, it's 20% less if you use the fixed threshold on a daily basis versus on a monthly basis. You also hear you see the standardized Streamflow index aggregate over 1 month. It's not so different, a little bit larger than the fixed threshold and the variable threshold method. In many cases, the standardized Streamflow is closer to the variable threshold than to the fixed threshold. So let's have some conclusions. As expected, the characteristics of streamflow droughts derived with different approaches, they deviate. So that's not a surprise. The only thing is that we have presented here a larger set of identification approaches, and we systematically applied it in Europe. The daily methods, they evidently generate more drought, 24 to 50% more than monthly drought, and of course there's an issue with minor drought, smaller than 30 days, as we have shown. If you look to the to end users, what can you advise then? If you would like to take seasonality into account, so that there could also be droughts in the high flow seasons, and the variable threshold or the standardized Streamflow index should be used. When drought deficit volumes are required by the end users, then the standardized approach can't be selected because it's not in the concept. All these actually results can be you can have a look at it in more detail in a paper which is in discussion in SD, and the impact of these drought identification approaches on the streamflow forecasting are presented on Friday afternoon by my colleague Sutanto. And thank you for your attention.